For as long as humans have gazed at the stars, Mars has been our mirror in red. It glows in the night sky like a distant ember, steady and alive, close enough to stir imagination, yet distant enough to remain mysterious. In ancient myth, it was the god of war, a fiery wanderer. In the telescopic age, it became something else, a world of possibility. When 19th century astronomers sketched faint linear markings across its ochre disk, some believed they were canals, the handiwork of a dying civilization. That dream endured for nearly a century, a world that was once blue and green, fading to dust. By the dawn of the space age, the question was no longer, is there life on Mars? But when will we find it? NASA's first robotic emissaries approached Mars in the 1960s. Mariner 4 in 1965 flew by and sent back 21 haunting photographs, the first close-up images ever taken of another planet. They shattered the romantic vision. No canals, no oceans, only a cratered, frozen desert. The myth of a living Mars evaporated overnight. But the data also revealed a world with an atmosphere, polar caps, and geological complexity. Beneath the disappointment, curiosity grew. Mariner 9, arriving in 1971, became the first spacecraft to orbit another planet and watched as a global dust storm engulfed Mars for months. When the haze lifted, the cameras revealed something no one expected: the largest volcano in the solar system, Olympus Mons, rising 22 kilometers above the plains, and a canyon system, Valles Marineris, stretching 4,000 kilometers long. The planet might be cold and airless, but it was also magnificent. These revelations prepared the way for NASA's boldest leap yet, the Viking missions. Launched in 1975, Viking 1 and Viking 2 each carried both an orbiter and a lander. Their mission was not only to study geology, but to answer one of humanity's oldest questions. Is there life on Mars? When Viking 1 touched down on Chryse Planitia on July 20, 1976, exactly 7 years after Apollo 11's moon landing, it became humanity's first successful landing on the red planet. The images it transmitted back were stunning in their simplicity, a landscape of rocks, dust, and distant hills under a salmon sky. For the first time, another planet had a horizon we could stand upon, if only through a robot's eyes. The Viking landers conducted a suite of experiments designed to detect biological activity. They scooped Martian soil and exposed it to nutrient-rich solutions, hoping to detect the gas exchange that would betray living microbes. One experiment, the labeled release LR test, did detect a reaction. Carbon dioxide was released when the soil was moistened, as if something inside were metabolizing. But the gas chromatograph mass spectrometer, designed to detect organic molecules, found none. The contradiction puzzled scientists. Was it life or merely chemistry? The consensus at the time leaned toward the latter, a false positive caused by highly reactive compounds in the soil. Despite the ambiguity, Viking's impact was enormous. Its orbiters mapped the planet at high resolution, revealing dry river valleys, delta-like formations, and layered terrain suggesting long-vanished floods. The idea that water once flowed on Mars, perhaps even pooled into lakes and seas, took root. But the instruments found no ozone layer, no liquid water, and an atmosphere less than 1% as dense as Earth's. Mars seemed dead. A beautiful, frozen ruin. The disappointment was deep. For nearly 2 decades after Viking, Mars faded from the center of NASA's ambitions. The 1980s became the quiet years, dominated by orbital missions closer to home. Yet a few scientists never stopped studying the Viking data, and their persistence kept Mars alive in the imagination of future explorers. In 1996, that imagination ignited again. NASA announced that a meteorite found in Antarctica, ALH 84001, believed to have come from Mars, contained microscopic structures resembling fossilized bacteria. Though later disputed, the claim rekindled global fascination. The red planet, once declared lifeless, was back in the headlines. It was time to return. That same year, NASA launched Mars Pathfinder, a mission that would mark the dawn of the robotic renaissance. Landing on July 4, 1997, in Ares Vallis, Pathfinder deployed a small six-wheeled rover named Sojourner, humanity's first moving explorer on another planet. Barely 65 centimeters long, Sojourner crawled across the Martian surface, analyzing rocks and sending back panoramic images that captivated millions. For the first time since Viking, Mars felt real again, not as a distant dream, but as a place we could visit. Pathfinder's success proved that low-cost, high-return missions were possible, ushering in a new era of exploration. Next came Mars Global Surveyor, 1997 to 2006, which mapped the planet in exquisite detail. It revealed signs of layered sedimentary formations, ancient river deltas, and minerals that form only in the presence of water. The evidence was building toward a new paradigm. Mars was not merely once wet. It had been geologically active, with cycles of volcanism, erosion, and perhaps even climate change. By the early 2000s, NASA's twin rovers, Spirit and Opportunity, carried the search forward. Landing weeks apart in 2004, they were designed to last 90 days. Spirit survived 6 years. Opportunity, nearly 15. Their cameras and spectrometers found hematite blueberries, tiny spherical concretions formed by water, and layered rocks shaped by ancient streams. For the first time, scientists could point to direct physical evidence of past liquid water. Mars had not always been a desert. It had been a world with rivers, lakes, and possibly shallow seas. Spirit's discovery of silica-rich deposits at Jezero Crater and Opportunity's detection of sulfate minerals in Meridiani Planum confirmed a complex geologic past shaped by water and wind. These rovers transformed Mars from a myth into a dynamic planet with a biography, one that once may have nurtured life. Then, in 2008, NASA's Phoenix lander touched down near the North Pole. Its robotic arm dug into the soil and within days uncovered bright patches that sublimated away. Water ice, exposed for the first time on camera. Phoenix also found perchlorate salts, chemicals capable of both supporting and destroying organic molecules. The planet was revealing its paradoxes again. Where water might exist, chemistry might conspire against life. By the time Curiosity launched in 2011, NASA's strategy had shifted from searching directly for life to searching for habitability, the conditions that could have supported life in the past. Curiosity, the size of a small car, was the most sophisticated rover ever built. It carried laboratories on wheels, SAM, sample analysis at Mars, and Chi-Min, chemistry and mineralogy, capable of analyzing rock powder for organics and isotopes. Curiosity landed in Gale Crater on August 6, 2012, using the daring sky crane system that lowered the rover by cables before the descent stage flew away. It was one of the most audacious landings in aerospace history. The first image, the rover's shadow stretching across the Martian surface, became an icon of modern exploration. Almost immediately, Curiosity began uncovering signs that Mars had once been warm and wet. Ancient stream beds with rounded pebbles, mudstones formed in long-standing lakes, and chemical traces of sulfur, nitrogen, and carbon, the building blocks of life, painted a portrait of a planet that might once have been blue. In 2013, Curiosity drilled into rock layers at Yellowknife Bay and found clay minerals formed in neutral water, neither acidic nor alkaline, an environment that could have been hospitable to microbes. Then came the discovery of organic molecules in 2018. Curiosity's instruments detected complex carbon compounds preserved in shale-like rock. While not proof of life, these molecules were tantalizing. The kind of chemistry from which biology could emerge. Coupled with evidence of ancient methane fluctuations in the atmosphere, they hinted at processes still active beneath the surface. Through these successive missions, NASA's approach to Mars evolved from exploration to investigation, from curiosity to continuity. Each robot was not an isolated experiment, but part of a lineage, each building upon the discoveries of the last, each asking more precise questions. From Viking's ambiguous experiments to Curiosity's confident geochemistry, the focus had shifted from "Is there life now?" to "Was there life once, and could there be again?" And so Mars, once imagined as home to canals and civilizations, has become a mirror of our own planetary past. It shows us what happens when a world loses its magnetic field, when its atmosphere is stripped by solar wind, when oceans retreat and deserts rise. It is both a warning and an invitation, a planet that failed to remain alive, yet may still harbor the seeds of possibility. The Red Planet's story is one of patience, of decades-long pursuit across silence and dust. From the lonely hum of Viking's instruments to the tireless wheels of Curiosity, every mission has been a step across time, as well as distance. What NASA found on Mars was not a single discovery, but a revelation unfolding across generations. The persistence of life's question. And that question, still unanswered, leads us onward, toward Jezero Crater, where the next chapter of Mars exploration begins. Ancient rivers and organic clues, Jezero Crater and Perseverance rover discoveries. In the pale light of February 18, 2021, a new set of eyes opened on Mars. The spacecraft carrying NASA's Perseverance rover plummeted through the planet's thin atmosphere, its heat shield glowing like a miniature sunrise. 7 minutes of terror followed, an unbroken ballet of precision that transformed speed and fire into grace. When the dust settled, Perseverance stood upright in Jezero Crater, an ancient basin that once cradled a lake. For the first time in half a century, humanity's most sophisticated machine was ready to continue the search that Viking began. The search for life, not as myth, but as memory. Jezero Crater had been chosen for one reason: water. Billions of years ago, when Mars still had an atmosphere thick enough to sustain rivers and rain, a vast network of channels flowed into Jezero, forming a river delta. Orbital images revealed fan-shaped deposits of sediment, mineral layers, and carbonate rims along the crater's edge, telltale signatures of standing water. If life ever existed on Mars, Jezero was the kind of place it would have thrived. A calm lake bed, where nutrients, organics, and minerals mingled for millennia before the planet froze. Perseverance's mission was not to guess, but to collect the proof. Descending from its aeroshell, Perseverance used the same sky crane system pioneered by Curiosity. Cameras captured every moment, the parachute deploying, the rovers swinging gently on cables, the engines firing dust into scarlet plumes. For the first time in history, the landing of a spacecraft on another planet was filmed in full color and high definition. When Mission Control heard the words, "Touchdown confirmed," a world watched together. Mars was no longer a distant sphere of mystery. It was a place, familiar, reachable, waiting. Perseverance's first panorama showed what scientists had long imagined: a river delta frozen in time. Layered buttes and fan-shaped cliffs rose like the remnants of a drowned world, each stratum a page in the history of water. The rocks looked Earth-like in form, but alien in hue, golden, reddish, and pale blue-gray, shaped by currents that had not flowed for billions of years. The rover's mission was to decode this record, to analyze texture, chemistry, and mineralogy in search of signs that life once left its trace. Perseverance carried the most advanced suite of instruments ever sent to another planet. Its Sherlock spectrometer, scanning habitable environments with Raman and luminescence for organics and chemicals, could detect organic molecules by their faint glow under ultraviolet light. Its PIXL, planetary instrument for X-ray lithochemistry, could measure the chemical composition of rocks at microscopic scale. The supercam atop its mast could vaporize rock from a distance with a laser and analyze the plasma. And beneath the rover's belly lay a small metallic capsule of daring, a helicopter named Ingenuity. Ingenuity was meant to be a short experiment, 5 flights at most. On April 19, 2021, it spun its carbon fiber blades and rose into the thin Martian air, hovering 3 meters above the ground for 39 seconds. 39 seconds, the first powered flight on another world. That small leap changed everything. The helicopter would go on to perform more than 60 missions, scouting terrain, guiding Perseverance's path, and proving that aerial exploration was possible even under a sky less than 1% as dense as Earth's. In its shadow, a new dimension of Martian exploration was born. But Perseverance's true work was slow, methodical, and patient. It drilled into layered rocks along the delta's base, gathering core samples, cylinders of stone sealed inside titanium tubes. These would become the first specimens ever collected for return to Earth, a scientific endeavor spanning decades. The plan was unprecedented. Future missions, jointly operated by NASA and the European Space Agency, would send a lander to retrieve these samples and launch them into orbit, where a waiting spacecraft would ferry them home. Each tube would carry a fragment of Mars's story, perhaps even the fossilized chemical memory of life. The first major discovery came from the delta's floor. Perseverance's instruments detected igneous rocks, crystallized from molten lava rather than sediments, suggesting that Jezero's history was more complex than expected. The crater had not only hosted water, it had also seen volcanic activity. This meant scientists could date the layers precisely using radiometric methods, linking Mars's hydrological and volcanic history into a single timeline. More importantly, these rocks contained carbonates and olivine, minerals known on Earth to trap and preserve organic material. The lakebed might therefore act as a geological archive of ancient biosignatures. As the rover ascended toward the delta's edge, it found what orbital images had hinted at: fine-grained mudstones and clays shaped by slow-standing water. Within these rocks, the SHERLOC instrument detected complex organic molecules, aromatic carbon compounds that form the backbone of life's chemistry. These molecules are not necessarily biological, but their abundance and structure were striking. Combined with the mineral context, clays, carbonates, and sulfates, they indicated that Jezero's waters were neutral to mildly alkaline, rich in nutrients, and stable for long durations. It was the most habitable environment ever confirmed beyond Earth. Adding to the intrigue were observations of sedimentary cross-bedding and ripple marks, the geological fingerprints of flowing rivers. High-resolution images revealed delta channels stacked atop each other, carved by varying water levels. The pattern suggested that Mars once had a sustained hydrological cycle: evaporation, rainfall, and river flow, rather than isolated floods. The climate that sculpted Jezero had lasted long enough for lakes to fill and drain repeatedly, perhaps over millions of years. Perseverance's instruments also sniffed the air. Its tunable laser spectrometer detected variable levels of methane, though still at trace concentrations. Methane is tantalizing because on Earth it can be produced by both geological and biological processes. The fluctuations over time hint at sources beneath the surface, possibly sealed pockets venting gas into the atmosphere. If confirmed, it would suggest active chemistry, or even microbial metabolism, persisting today. Meanwhile, Ingenuity's reconnaissance flights revealed fractured ridges and sand-filled channels unreachable by the rover's wheels. These bird's-eye views gave scientists a map of Jezero's complex terrain, identifying regions rich in layered deposits that may contain the best-preserved biosignatures. For the first time, exploration combined the perspectives of rover, aircraft, and orbiter, a choreography across scales of space and time. By 2023, Perseverance had drilled more than a dozen samples, each catalogued and cached along a flat plane for later retrieval. Among them were rocks that glowed faintly under Sherlock's ultraviolet light, potential carriers of organic residues. Others held sulfate salts that crystallize only as water evaporates, sealing inside them the chemical memory of ancient lakes. The Mars Sample Return Campaign aims to bring these relics home by the early 2030s. When they arrive, scientists will study them with instruments too delicate to send across space: electron microscopes, isotope analyzers, and spectrometers capable of detecting traces of once living molecules at the part-per-trillion level. The results could confirm what Viking glimpsed and what Curiosity hinted, that Mars, long ago, was alive. Yet even without that ultimate answer, Perseverance has already redefined our image of Mars. The planet once thought dead now appears chemically dynamic, shaped by water, wind, and time. Its deltic formations mirror those of Earth's great rivers, the Nile, the Mississippi, the Tigris. The difference is not form, but fate. Where Earth's rivers feed oceans, Mars's rivers ended in silence, frozen before they could return to the sea. And in that silence lies the story Perseverance was built to tell. Every day on Mars is a study in contrast, a world where ancient beauty meets relentless cold. Dust devils swirl across crater floors. The sky fades from peach to violet at dusk. Perseverance's tracks cross rocks older than continents, its cameras capturing the slow ballet of Martian light. Through its eyes, we see not an alien desert, but a memory of home. A planet that might once have looked back at us across the void, alive and blue. And in the thin Martian twilight, a small helicopter still flies. Ingenuity, long past its expected life, continues to leap across Jezero's plains, each flight a whisper that flight itself, and life perhaps, can find a way, even on the most desolate of worlds. For NASA, Perseverance is not the end, but the bridge, the point where robotic exploration meets human ambition. Its discoveries are the scaffolding of what comes next: habitats, laboratories, and footsteps on the red dust. The rover's cameras gaze toward the delta's rim, where cliffs rise like the shores of an ancient sea. One day, human eyes will look from that same place, not through a lens but through a visor, and the circle will be complete. Preparing for humans, the coming era of Martian colonization. From the moment Vikings' cameras captured the first Martian horizon, a single question has burned at the edges of human imagination. When will we go there ourselves? For decades, Mars was the next logical step. A world so Earth-like that it seemed almost destined to be inhabited. Yet the gulf between imagination and reality was immense. Its thin air, lethal cold, and radiation-bathed surface made it more hostile than any desert or ocean ever crossed by humankind. Still, with every rover that rolled and every discovery that hinted at ancient rivers, the idea of going to Mars began to shift, from fantasy to engineering problem. NASA's path to Mars was never a sprint. It was a gradual construction, a ladder built from lunar footholds, robotic scouts, and generations of evolving technology. The Artemis program, by design, serves as that first rung. What humanity learns on the moon about resource extraction, radiation shielding, and long-duration living in reduced gravity will define the architecture of Mars missions. In NASA's language, Artemis is the proving ground. Mars, the horizon. The experience of surviving on the lunar surface, with its extremes of temperature and isolation, will prepare astronauts for the months of interplanetary travel and years of exile that Mars demands. The logistics are staggering. A round-trip mission to Mars will take roughly 2.5 years, 6 to 9 months to travel there, 500 days on the surface, and another 6 to return, depending on planetary alignment. Every kilogram of cargo must be justified. Oxygen, water, and fuel cannot all be brought from Earth. Instead, NASA's plan centers on in situ resource utilization, ISRU, extracting what is needed from the planet itself. Experiments aboard Perseverance have already tested this concept. The small device known as MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, successfully converted carbon dioxide from the Martian atmosphere into pure oxygen, about 10 grams per hour, enough for an astronaut's short-term use. Scaled up, this technology could supply breathable air and oxidizer for rockets, turning Mars's atmosphere into fuel. Equally critical is water. Orbiters and landers have identified vast deposits of subsurface ice, especially at higher latitudes. Future missions will target these frozen reservoirs, using robotic drills and heating systems to melt and purify water for consumption, agriculture, and hydrogen extraction. This dual use, life support and propulsion, forms the backbone of Mars' sustainability. What once made the planet inhospitable may soon make it habitable. Its carbon dioxide atmosphere, its frozen poles, its minerals rich in oxygen and metals. Mars is harsh, but it is generous in the right hands. The habitat concepts under development resemble a fusion of science fiction and pragmatic design. Inflatable modules, buried beneath regolith for radiation protection, could form the first bases. Underground lava tubes, vast natural tunnels formed by ancient volcanic flows, might serve as ready-made shelters, offering insulation against cosmic rays and temperature swings that range from plus 20 degrees Celsius by day to minus 120 degrees Celsius at night. Solar power will dominate early operations, but small nuclear reactors, like NASA's kilopower prototype, will provide continuous energy through the 14-hour Martian night. Food, too, will require innovation. Hydroponic and aeroponic systems will recycle water and nutrients to grow plants under LED light, while waste is converted to fertilizer and methane fuel. NASA's ECLSS, Environmental Control and Life Support System, perfected aboard the International Space Station, already recycles 98% of water used by astronauts, urine, sweat, condensation, closing the loop of survival. The same principle will define Mars bases. Nothing wasted, everything repurposed. Transportation across the planet will depend on pressurized rovers and eventually small aircraft. Concepts for nuclear electric vehicles capable of traversing thousands of kilometers are already in study, as are autonomous construction robots to assemble habitats before human arrival. The goal is permanence. Not a single footprint, but a settlement that can expand. At the heart of NASA's plan is Starship, SpaceX's fully reusable super heavy vehicle designed to carry 100 tons to Mars. Starship's vision aligns with NASA's architecture, its stainless steel hull doubling as both spacecraft and habitat. Elon Musk's company envisions fleets of them, armadas departing every 26 months when Earth and Mars align. These ships could carry cargo first, habitats, power systems, supplies, followed by the first human cruise. For NASA, Starship serves as the bridge between public agency and private innovation, a partnership where government exploration meets entrepreneurial ambition. Radiation remains the most formidable challenge. Without a global magnetic field, Mars is bombarded by cosmic rays and solar storms that could deliver fatal doses over time. Engineers are exploring hydrogen-rich shielding, walls lined with water or polyethylene, and even electromagnetic deflectors that mimic a mini magnetosphere. Deep within lava tubes or regolith-covered domes, astronauts could find sanctuary. Long-term missions will also rely on artificial gravity, perhaps through spinning habitats or tethered spacecraft, to combat muscle and bone loss during transit. Every aspect of Mars colonization is being reverse-engineered from the physics of survival. Beyond the engineering lies the psychological frontier. Mars is a mirror not only of our technology, but of our endurance. Astronauts will face isolation unlike any experienced before. Communication delays of up to 22 minutes each way, an entire world separating them from home. NASA's analog missions in desert habitats, such as HICs in Hawaii and NEK in Russia, have simulated this solitude, teaching how teams adapt to confinement, monotony, and reliance on one another. Mars will test not only the body, but the human spirit, whether we can create society in a place without air, rain, or horizon. In NASA's long-term vision, Mars will evolve from outpost to colony, then to civilization. The first explorers will land near water-rich regions, establishing temporary bases powered by solar arrays. These will grow into permanent settlements, linked by transport corridors and supply chains. Future habitats may cluster near equatorial canyons or volcanic plains where ice and minerals lie close to the surface. Robotic miners will extract metals, while greenhouses expand into self-sustaining ecosystems. Over decades, Mars will cease to be a destination and become a second cradle of humankind. The dream of terraforming, reshaping the planet's climate, remains distant, but not dismissed. Ideas abound, releasing greenhouse gases to thicken the atmosphere, redirecting comets to deliver water, or deploying orbital mirrors to warm the poles. Most scientists agree full-scale terraforming is centuries away, but even small-scale geoengineering, local habitats with contained ecosystems, could make Mars incrementally more livable. The first steps will not turn the planet blue, but they will turn parts of it green. Philosophically, the human journey to Mars is about more than survival. It represents the next step in cosmic continuity, life extending beyond its birthplace. Every instrument that has touched Martian soil, from Viking's sampler to Perseverance's drill, has carried this hidden purpose: to prepare the way for us. The transition from robot to human marks the fulfillment of a century-long arc, from telescope to footprint, from observation to presence. NASA's proposed Mars Base Camp envisions a fleet of orbiting spacecraft supporting crews on the surface, relaying data in real time, and serving as launch pads for deeper missions. The base would integrate with the Lunar Gateway, ensuring continuous transport between Earth, Moon, and Mars. Each world becomes a node in a growing web, the architecture of an interplanetary civilization. Private industry sees the same horizon. SpaceX's Mars plans, Blue Origin's lunar infrastructure, and international efforts from Europe, China, and the UAE are converging on the same idea: that Mars is not just the next step for one nation, but the inheritance of all humanity. The planet is a blank page, a chance to rebuild society from first principles, to test sustainability, governance, and ethics in a new environment. And yet, beneath the excitement lies reverence. Mars is an ancient world, older than any city, shaped by wind and time. To walk there is to trespass on eternity. The first astronauts who step onto its soil will not merely plant a flag. They will kneel to touch a surface that remembers before there was life on Earth. They will breathe oxygen drawn from alien air, drink water melted from frozen time, and see Earth as a star. The future imagined in science fiction, domed cities glowing under red skies, ships lifting through pink dawns, begins here, not in fantasy, but in engineering diagrams and launch manifests. Each line of code, each test firing, each orbiting relay is a thread in humanity's first interplanetary tapestry. When that first crew returns to Earth, their journey will redefine what it means to be human. They will have lived under 2 suns, seen 2 moons rise, and walked where no life has walked in billions of years. And perhaps in the dust beneath their boots, they will find evidence that life came before them, a message from a time when Mars was alive and Earth was young. Mars will not be conquered, it will be joined, a partner in our continuing story. The red frontier, once silent, will echo with voices again. In that echo lies the truest discovery of all, that exploration is not about where we go, but about who we become when we get there.